Okay. If you want to turn your cameras on, that'd be great, but if you don't want to, that's also fine. So, um, I want to begin with, hope you can see me and hear me. Is that okay? Let me check that before we begin.
Yeah.
Yeah, lovely. Okay, perfect. Hello, everyone. I'm Arya. I'm the Chief Scientific Officer of the Global Society of Physicists and the co-creator and the coordinator for the Research Mentorship Programme. I'm also the mentor for the quantum mechanics course. Just to make sure you all agree, this recording and some bits of the other recordings might be shared on various media channels, like the GSYP Instagram, LinkedIn, and our website. So before we begin, I want to talk about the foundation of GSYP first. Um, Before we do that, I want to check something. Okay. So when I was around your age, I went to summer school for quantum cryptography called QCSIS. Now QCS is called at the University of Waterloo. The program was fantastic with fantastic lecturers, and it was unforgettable for me. So with some of the friends I made from there, most importantly Leo, who couldn't be here today, we founded GSYP as a platform to connect young physics enthusiasts. We also entered to a competition called Beam Line for Schools from CERN. I don't know if you heard about it. I think some of you participated in it as well because you're all high school students. We participated in that contest, in that competition, with an experimental paper called it has a mouthful name. It's measurement of thermal conductivity of thin and thick layer graphene via phonon dispersion by inelastic X-ray collision produced through Bremsstrahlung radiation. So we entered the competition with this mouthful title. Anyway, it was a wonderful experience as we did this project together, but we didn't have a mentor at all. We reached out to professors, PhD students, but nobody was willing to help because they were all students from across many continents, and that's why we were lost about who should help us. I thought students who want to do a research project should be able to find mentors, and there should be a summer program with a purpose for them to collaborate together. So as we're doing now. So because my biggest passion is research, and I think all of you have the same passion as well. Hence, we founded this program within GSYP. So today, we're all gathered here, physics enthusiasts, interested in research in various physics topics after 5 hectic weeks of lectures, problem classes, and research. But I commend the outstanding work all of you have put forward. It is beyond incredible, to say the least. I'm sure you all have bright futures ahead. I also commend your mentors here for the incredible work they put forward as lecturers and guiding you through your research. Their efforts are what made tonight possible in many, many ways. As your mentors, we're all from King's College London, so if you're around London or the university, I would speak for myself here, and I would say let me know and we can catch up. But I think your mentors would be happy to do that as well. Okay, so it was a full 5 weeks of cosmic objects, practical applications of physics, looking into the mathematical aspect of it, and physics of the super, super small quantum, Alice in Wonderland. So let's begin your final day presentation as RMP 2024 concludes tonight. So at first, let me just check the lobby if there's someone waiting in the lobby. I don't think so. Okay, then we can move on. So I will go alphabetically, as I always mostly do. It will be cosmology students first, but before I hand over to the students, I want to hand over to your mentors for their input first. I don't think Duke is here. Is he here?
I do not
No.
see him.
Okay, then I'll just hand it over to you, Toby,
Brilliant.
for your
Well,
input.
I wanted to just, well, what a nice speech to start us off with. I think we'll all agree. wanted to say that really, although it may be down to the mentors to make sure that the ship sails, there would be no ship without Arya building it in the first place. So big hand to her for that. Our students are amazing. I was quite frankly blown away with how bright and driven and just impressive this cohort that I've led has been, and I'm very proud of them, and especially of this last research paper which you're going to see. Our topic, or I should say their topic, is the Higgs mechanism, the Higgs boson, the Higgs everything, and we encountered this briefly through my side of the teaching, as we talked about things like cosmic inflation and false vacuum theories, and touched upon Peter Higgs' groundbreaking work in that field. I would argue one of the most monumental discoveries at CERN, definitely sort of the crown jewel, if you will, of their work. A really, really important moment in physics when that was discovered. However, Higgs himself was ever the most humble man. My favorite quote of his is that upon publishing this paper that detailed the Higgs boson, he said, "Today I have discovered something totally useless." So in his memory, I'm going to hand over to my students to talk through their wonderful research on the Higgs mechanism. Take it away, guys.
No, okay, thank you for your words. I'm going to share my screen. Okay, can you see the presentation?
Yeah.
Okay, thank you. Okay, so we focused on the Higgs boson, as Toby said, and let's start. Let's start our presentation. Yes.
Okay, so good evening, everyone. So today we will be presenting our research on the Higgs mechanism and its significant implication for cosmology. So we choose to focus on the Higgs boson because of its fundamental role in particle physics and its profound impact on our understanding of the universe. We trace the historical and theoretical development of the concept, emphasizing the contribution of Peter Higgs and others. Our study explained the theoretical foundation that led to the prediction of the Higgs boson and its importance in explaining particle mass. We also highlighted experimental confirmation by the ATLAS and CMS collaborations at the Large Hadron Collider. And additionally, we explored the cosmological implication, particularly the Higgs mechanism impact on the early universe evolution and the formation of large-scale structures. So by integrating theoretical insights with experimental evidence, our research underscored the profound significance of the Higgs mechanism in contemporary physics and cosmology.
Okay, I will do just a brief introduction. The Higgs mechanism was firstly proposed by Peter Higgs and some of his colleagues in the 1960s. And it's a crucial theory for the standard model because, as we will see, it like fixed some problems that arose from previous theories. In 2012, the discovery of the Higgs boson by the LHC, the Large Hadron Collider experiment at CERN, confirmed that theory, marking an historical milestone in science and physics in particular.
So, hello everyone, let's talk about the properties of Higgs boson. So, its first property is about mass, and it is approximately about 125 giga electron volt. And its mass was confirmed by experiments at the Large Hadron Collider in 2012. And here we have a small expression that shows m to the power 2h which is equals to 2 times lambda v to the power 2. And on substituting v approximately 246 GeV, we get the mass 125 GeV, and it is experimentally measured. And second one is about spin, and it has spin 0. And we know that Higgs boson is a scalar particle, so which means that it has no intrinsic angular momentum. And next one is about charge, and Higgs boson is electrically neutral, so it has a 0 electric charge. And similarly, we have about parity. So Higgs boson is a scalar field excitation which contributes its positive parity. Therefore, its parity is +1. And about its decay modes, it decays into various particles, including photons, double and jet bosons, and fermions like quarks and leptons. So next slide, please. So here we can see the diagrams of the standard model Higgs boson decay, and another figure is about a charged Higgs boson production.
Okay, now I will try to explain the Higgs mechanism. The Higgs mechanism is one of the most important aspects of modern physics because it answers a very fundamental question. That is, why do particles, or some particles, have mass? It may seem a trivial question, but actually scientists, and Peter Higgs in particular, have tried so hard to answer this. So why do we need an Higgs particle, an Higgs boson, and an Higgs mechanism in the first place? Well, we need it because some of our previous theories didn't work as they should. I'm talking about the electroweak theory. According to this theory, the electromagnetic and the weak interactions can be unified into a unique force, a unique interaction, the electroweak one. So according to our previous model of the electroweak interaction, in order for the theory to respect the gauge symmetries that are some transformation of some mathematical parameters that leave the physical description of a phenomenon unchanged. So in order to respect these symmetries, the W and the Z bosons, some that are the vectors of the weak interactions, had to be massless. Unfortunately, we saw from the various experiments of particle physics that these two particles have, in fact, mass. So we needed a new theory to explain why we observe a mass that shouldn't be there according to our theory. So let's start from a very important equation in quantum mechanics. That's the Klein-Gordon equation. You can see that in the screen. Oh, can you see the blue dot? Can someone confirm that you see the blue dot?
Yes, we can.
Okay, thank you. So this equation is related to the very famous Einstein's relativistic energy momentum equation that you can see here. So the Einstein one says that the energy of a particle squared is equal to its momentum squared times the velocity of light squared plus the mass of the particle squared times the velocity of light to the fourth power. So similarly, this equation contains the most important information about a quantum particle or field, such as its energy, momentum, and mass. Speaking about the mass, if phi, this one Greek letter at the end, refers to quantum wave, then the mass is the mass of the particle. While if like in this case, in this scenario, phi is a quantum field, m is the mass of the excitation of the field. That is its particles. So thanks to this equation, we can describe a quantum field. Now we will consider two interacting fields, namely phi1, whose particles are massless, no mass, and phi2. This in the screen is the Klein-Gordon equation for the first one. As we can see, there is a new term, K12 times phi2 squared, that accounts for the interaction between phi1 and phi2. In fact, we're considering two interacting fields. And also, there is a term missing. We don't have the mass-related term, because, as I said, the phi1 field is massless. Its particles have no mass. So that's what our previous theory said. Thanks to this new interaction with the phi2 field, we have this new term, this new positive term. So we can see the similarity between this term, and the new term we added. It's a positive addend that plays the same mathematical role as the previous one. Thanks to this interaction, we can explain how the particles of the phi1 field acquire mass, have mass. We just need to make sure that this is a non-zero term. This means phi2 must be non-zero, since K12 is a non-zero constant. To do that, let's consider the Klein-Gordon equation for phi2. So the first equation in the slide. The problem is that phi2 is equal to 0 is the only solution to this equation, and that's exactly what we want to avoid. So we need to think of something some particular characteristics. For example, we may think of a field interacting with itself. So now we have a new term, K22 times phi2 squared, that accounts for the self-interaction of phi2. So now we have a new Klein-Gordon equation. Let's try to find the solution. Phi2 is equal to 0 is again a solution. We have two more solutions that are found calculating this equation. So the last two terms inside the parentheses are equal to 0. We can do this because in order for the solution to be stationary, the first two terms, so these two, must be equal to 0. So we can consider just these two. This is just a quadratic equation with two solutions that you can see in the bottom of the slide. So phi2 is equal to plus or minus the square root of minus m2 squared times c squared, so the mass of the field, of the particles of the field squared, times the velocity of light squared, over the reduced Planck constant squared, times the interacting constant, K22. We have now three solutions for phi2. We have to be sure that we can discard the null solution, the phi2 is equal to 0 solution. To do that, we can consider the potential energy U of the system. And it turns out that the graph that you can see on the screen is the graph of the potential energy against various values of phi2. As we can see, that the null solution, so phi2 is equal to 0, corresponds to a maximum value of the potential energy. And that value, a maximum value for the potential energy, is an unstable condition. Hence, we can discard the phi2 is equal to 0 option. So now we are left with two solutions that are non-zero. So we are sure that this term, the k1 2 times phi2 squared in the Kling-Gordon equation for phi1 is non-zero. As a result, we can conclude surely that after the interaction with phi2, phi1 does in fact get mass. In this little example, phi2 is the Higgs field. Furthermore, the assumption that we have made that the Higgs field is self-interacting is actually true. We have discovered from the various experiments that the Higgs boson has mass, and that means that it interacts with its own field.
So, okay, let's now talk about Higgs boson and its implication. So, the Higgs boson is a cornerstone of a standard model of practical physics, and actually it helps in describing the fundamental particles and forces in the universe. And similarly, it also helps in understanding the conditions of the universe and the evolutions of the cosmos, and some properties of the Higgs boson could have implications for cosmological models which are relating to different subject matters like dark matter and dark energy. And not only that, it opens new avenues for research which might eventually lead to new discoveries and astonishing theoretical insights.
So the research of the Higgs mechanism started with the idea of spontaneous symmetry breaking, which was introduced by Yoichiro Nambu in 1960. Let's explain this idea. So every quantum field has a potential energy which reaches its minimum at the vacuum state. A graph representing the potential of the field against its force had a parabolic shape at the beginning of the universe, as we can see in the graph at the right. But then at the electroweak phase transition, which happened 1 picosecond after the Big Bang, the shape of the graph changed into another symmetric shape, which had two minima instead of one. So it had two vacuum states instead of one. The impossibility of the universe of being at two vacuum states at the same time caused the symmetry to break. Next slide, please. So the potential of the Higgs field has 3 dimensions and can be called a Mexican hat potential because of its shape. The phase of the field, meaning its angular position around the brim of the hat, can change without a cost in energy. So from here, a rotational symmetry emerges. In 1961, Goldstone theorem was proved, and this theorem states that spontaneous breaking of a global symmetry, such as this rotational symmetry, leads to the appearance of one or more Nambu-Goldstone bosons. These are particles which are presumably massless and spin zero. Next slide, please. But then in 1964, Peter Higgs proposed the existence of a massive boson associated with the field. And then the experimental search of the Higgs boson began in the 80s at Deutsches Elektronensynchrotron and then continued at CERN's Large Electron-Positron Collider. One of the experiments at Large Electron-Positron Collider, called Aleph, observed a series of events resembling a Higgs boson with a mass of 115 gigaelectron volts by c squared. Next slide.
So the Higgs boson was discovered in 2012, nearly 50 years after it was first theorized, and the long search for this particle is due to its significant mass, over 120 times that of a proton, and its extremely short lifespan. This means that the Higgs boson cannot be found naturally, and it must be produced in a laboratory, specifically in a particle collider like the Harge-Lider Collider, the world's largest and most powerful particle accelerator located near Geneva, which began operating in 2010. Next slide, please. Next slide, please. So the ATLAS experiment is one of the principal pillars of the LHC. ATLAS is a multi-purpose particle detector with a forward-backward symmetric cylindrical geometric. The detector records digitalized signals produced by the products of LHC proton bunch collisions, hereafter termed collisions events. The research entails a significant challenge in discriminating between Higgs boson decay products and those originating from a multiple of concurrent collision events, owing to its rarity of occurrence. So by the time of the Higgs boson discovery announcement, scientists analyzed data from around 300 trillion proton-proton collision, and out of these collisions, the number of the Higgs boson events observed was 500, highlighting the challenge of detecting such a rare particle. Next slide, please. So scientists analyze many collisions and measure a quantity called invariant mass from the detected particles. And for Higgs decay products, this mass matches the Higgs mass consistently. And by analyzing a large number of collisions, we can identify a slight excess at a specific invariant mass, indicating the Higgs boson presence. On 15 June 2014, ATLAS physicists produced their first measurement of the mass of the Higgs boson, and their paper studied all available LHC collision data at the time, looking at the Higgs boson, its decays to 2 photons and into 4 leptons. Next slide, please. So as I talk about the Higgs boson decays, the decay of the Higgs boson encompasses several distinct channels, so each revealing crucial insights into its interactions and properties. For example, we have the gamma-gamma decay, which the Higgs boson decays into 2 photons. We have the ZZ decay, in which the Higgs boson subsequently decay into 2 leptons or quarks. We have the WW decay, in which the Higgs boson decays into 2 W boson and further decays into leptons or quarks and neutrinos. We have the BB decay, in which the Higgs boson frequently decays into a bottom quark and its antiparticle. And then we have the tau-tau decay, in which it decays into 2 tau leptons, but also the upsilon decay, in which the Higgs boson decays into a pair of upsilon mesons. Next slide, please. And here you can see listed are the measured decay modes, target production processes, and integrated luminosity, and the various decay modes of the Higgs boson. Next slide.
So did the man manage to join the meeting, or?
So, yeah, the Higgs field in cosmology is a combined idea, unified the physics of the Higgs field with the cosmological phenomena to explain the early universe. So, since our knowledge about the Higgs field is a scalar field, and we have discussed before that the inflation happened because of a potential energy. So, the Higgs field was thought to be the inflaton that happened the inflation. Next slide. So the standard potential energy in the Higgs field is formulated by this formula, but this wasn't applicable for the Higgs field to code the inflation because it wouldn't allow the slow roll condition. So the slow roll condition will add more time for the inflation to happen, which will make the universe expand. So it has to be minimal with the gravity. It should be coupled with the gravity. Next slide. Okay. For the Higgs field to be coupled with gravity, it was expressed by 2 ways. First, minimal coupling is the simplest interaction between the field and the gravity involving only space-time metric. In the scenario of minimal coupling, the Higgs field interacts only with space-time fabric curvature in a straightforward manner. Potential must be extremely flat, and that's can't happen naturally. So that's why the non-minimal coupling was expressed. When the next slide.
Non-minimal coupling adds the curvature of space-time, and that gives more potential energy to the field to drive the inflation, and wouldn't make it happen so fast, so it can expand. And that was adding the Ricci scalar that Einstein expressed in his equation of special relativity. That's all.
So the Higgs mechanism and the kinematics of the production of the Higgs boson have proved to be in agreement with the predictions done by the Standard Model, according to the experiments performed in ATLAS from 2015 to 2018. However, measurements of some of its properties still need to be done. The Higgs mechanism explains how elementary particles acquire mass, but not how dark matter does. As suggested in recent research, the idea of spontaneous symmetry breaking, which was thoroughly explored through our research, could be crucial to understand it. So dark Higgs field is a new possibility of study. Recent research proposes a reinterpretation of the Higgs mechanism, connecting it with quantum information theory and creating a mathematical formalism that relates the Higgs potential with quantum entanglement entropy. Next slide.
So the research examined the Higgs mechanism and rules in mass acquisition and the impact of particle physics and cosmology. It covered the theoretical foundation, the historical journey of the Higgs boson discovery, and the experimental method used in CERN and Large Hadron Collider by learning the Higgs mechanism and to inflation theory. The study highlights the importance of understanding the universe expansion. While significant progress has been made, ongoing research promises new insights of the fundamental nature and matter in the universe.
Okay, thank you for your attention. That was our research. Thank you.
Wonderful. Thank you to the cosmology team. Does anyone have any questions for the cosmology team? If you're raising your hand, I can't see you. So, okay, brilliant. So I have a question. Can you give us more insight on the dark Higgs you mentioned in your presentation, if you've researched on it?
The dark Higgs field.
Yeah.
Said?
We
We didn't really. Yeah. Go. Sorry.
We added it just as a possible expansion for our research, but it wasn't one of our main points, so we really didn't include it.
Okay, lovely. I was just wondering because your presentation was really interesting. Thank you for your kind words, Toby, as well. So Peter Higgs was truly an incredible scientist, and he was a King's College London alumnus as well. So we have a bunch of photos of him around the campus. Incredible work to the cosmology team. Your research shows a deep understanding of the subject matter, which is truly impressive. And since Duke is here now, would you like to add any input of your own as a cosmology mentor, Duke? I don't know if you can hear us. Okay, I'll move on.
Hi, sorry, I was trying to
It's
unmute.
okay.
I've nothing to really add. I read through your document yesterday and I thought it was amazing. I remember when I had to do the project with my uni colleagues and it was nowhere near as good as your guys. So really well done. Well done. Seriously.
Okay,
Thank you.
lovely. Thank you, Duke. Now I'll hand it over to the experimental and engineering students for the presentation of their research now. But first, I want to hand it over to their mentor, Pia. Over to you, Pia. If she can hear us.
Hi guys. Hi. So it has been 4 wonderful weeks looking into how physics concepts are applied experimentally and engineering fields, and it was really nice teaching everybody in my team. Good participation as well, and well done, like being active during your lessons as well, and you put your extra time, you worked, like you organized Zoom meetings amongst yourselves and everything, some with me, some without me, and extra time as well and everything, and finished everything on time. I'm so proud of you guys. Well done for that first. So my team worked on searching for magnetic monopoles. And even though it's a very theoretical side for now, they explored, researched on how we're currently experimentally trying to find things and how CERN is actively working on this. So they're going to give you better information than I would. So I'm going to hand them this opportunity. So good luck.
Thank you, Pia. And let me just share my screen. Yeah, can you see it? I never shared it here, so.
Yep, we can see it.
Yeah. So the search for magnetic monopoles, I think we can start.
Okay, so on research, we aim to review the current state of research in monopole detection, focusing on its current detection at CERN and previous ongoing research in the field. So magnets have always shared common characteristics, and is the fact that they are always dipole. They always have a north pole and a south pole. And even though we may think of the division, we still will get two smaller dipoles. Nevertheless, some physicists have predicted the existence of a magnetic pole which will have only one north pole or one south pole through theoretical approaches. This concept was first introduced in 1931 by Paul Dirac, and its existence will add symmetry to Maxwell equation, as well as it will explain why charge is quantized in nature. So experiments have taken place at the Large Hadron Collider at CERN, mainly using three mechanisms that are the Drell-Yan mechanism, the Schwinger mechanism, and the photon fission mechanisms that my mates are going to explain further.
So at CERN, during heavy ion collisions, magnetic monopoles are theorized to be generated with three methods, which is, as Susanna said, photon fusion, the Drell-Yan, and the Schwinger mechanisms. But in all three of these mechanisms, they hold the similarity that they're created with the same principle, which is fluctuations and vibrations in the magnetic monopole quantum field. So magnetic monopoles are 4/700 times the mass of a proton. So due to the equation E equals mc squared, the energy required for the creation of is huge. This means that the mechanisms where they are theoretically created have to be they have to have conditions of extreme energy and be just general extreme conditions. So obviously the LHC and heavy ion particle collisions at CERN are a very good method of this. But of course, they're accelerated to 99.99991% of the speed of light. And so, collisions between the heavy ions that are used are lead-208 ions. And these collisions are studied for monopoles. They're beginners 2 centimeter strips of just pure lead, not the ion itself, and only a few electrons are ionized with an electric current, and the rest of the electrons are ionized during initial acceleration before being injected into the LHC itself, because CERN is comprised of several different accelerators, but they go into certain ones before reaching LHC. LHC uses radio frequency cavities, or RF cavities, to accelerate the ions. They're designed to build up electromagnetic waves from beams of electrons, and they are built up to 16 megavolts per beam before they're released to accelerate the ions. So they accelerate the ions and to a point where they're passing through the RF cavities more than 100 million times over the course of around 20 minutes before they reach their max speed where they are collided. And the direction of the collisions is caused by, they use magnetic fields to direct the ions. So I've only really put two of the mechanisms in detail here. So the first one is the Drell-Yan process, and this happens during hadron-hadron scattering, which is essentially when the wave functions of two different hadrons from two different elements interact. So here, the annihilation of a quark and antiquark of different hadrons creates a virtual photon. Now, a virtual photon is a fluctuation in the photon quantum field, but it's less regular and it's more of a temporary fluctuation, whereas a normal photon would be a lot more steadier and a more regular fluctuation. So this vibration that creates a virtual photon, and then the virtual photon is decaying into a magnetic monopole particle-antiparticle pair. The next mechanism is the Schwinger mechanism. This is a newer mechanism that they're using at LHC. It occurs during heavy Miss ion collisions. So when the nuclei collide, the non-colliding nucleons are set a swirl, and because they're traveling so close to the speed of light, and they're obviously charged, these protons, they are generating magnetic fields that are the strongest fields in the current known universe. And these fields produce monopole pairs from the vacuum.
Okay, so this part delves deeper into the mathematical and physics implication of our research. So basically, in this research, we have a turning point, which is the year 1931, because in that year, Dirac started to hypothesize his theory of the quantization of charge. And before that, we mainly have two concepts that we delve deeper into our research project, mainly being Lorenz's equation, and the second one being how magnets are created, and in general the elements that we may see in magnets, especially with ferromagnetism and diamagnetism and paramagnetism. So basically, Lorenz's equation is the equation that states the force of electromagnetic field, which basically it ties together the vector of the charge, the vector of the velocity, and the electromagnetic field, being also a vectorial product. So basically, we could consider that force as a non-conservational force. And with that, the work technically would be zero, especially in moments where the vector of the velocity and the vector of the force itself, between them, it goes an angle of 90 degrees. So in that case, it would be a work that equals to zero. Since it's a non-conservational force, and the trajectory mainly is it's mainly a round trajectory, we could consider the Lorenz's force as a we could mainly consider it as a circular motion force, which leads it being to kind of a centripetal force. Especially in our research paper, we have also delved deeper into the concept and the demonstration of the radius of said trajectory. So the second part, as I said before, is how magnets are created. Magnets are created with this concept of the magnetization, where well, let's say an element, a ferromagnetic element or a diamagnetic element or a paramagnetic element, if we take a electromagnetic field and we strike it through this element, we can see how each atom inside of this of this element acts like a magnet itself. So the north pole and the south pole of these atoms basically align with the electromagnetic field outside. So at this point, we could consider if we take a magnet and decide to torn it apart, we can see how it would be kind of impossible for a monopole to create, and there would be only two little magnets. This until the Dirac's quantitization of electromagnetic energy, which is also present in the presentation, where we could see the equation of the product of E and G, E being the the electric charge, G being the magnetic charge, and being a general number that belongs to the mathematical set n, H being the reduced Planck's constant divided by 0. So these innuendos mainly include the quantitization of energy, as I said, the gauge symmetry, which is a type of symmetry where certain transformations do not change the fundamental aspects of said physical system, and especially with the grand unified theories. So now I'll give the floor to my teammate, Judy.
So as my friend Ellie mentioned, that we can detect monopoles first by generating them and then detecting them. There's a way that we can directly detect monopoles. This can be through three main aspects. The first one is using squids, which means superconducting quantum interference devices. The idea behind these devices is based on that when a magnetic monopole is passed through a conducting ring, it would induce a persistent change in current. The system attempts to maintain its original magnetic flux. This simply wouldn't happen in the case of a magnetic dipole or higher order magnetic pole, which the net induced current will be 0. So this is a direct detection of a magnetic monopole. Those superconducting rings provided a key benefit in the detection history of monopoles, where the capacity to maintain an induced current changes indefinitely without the dual heating inherent in conventional conductors. This innovation enabled more sensitive long-duration experiments, but early superconducting detectors were limited by the inadequate sensitivity of available current measuring electronics. The second way of detection of monopoles lies in the material-specific searches. The core of this aspect lies in the possibility that monopoles could exist in ordinary matter. Spin ice is constrained by crystal field effects to point either directly or toward, like either directly toward or away from the center of each tetrahedron. And the scientific relation between spin ice and magnetic monopoles arises from the concept of emergent excitations, which means that the elementary excitations in spin ice could be described as emergent magnetic monopoles. And we can say that the real connection between spin ice and magnetic monopoles is when a single spin in the spin ice structure is flipped, it creates a pair of defects that can be interpreted as a north and south magnetic monopoles. The third way of detection lies in the cosmology aspects. It states that meteors have been proposed as potential harbors for magnetic monopoles, but the high momentum of monopoles presents a challenge, as any meteor-trapped monopole striking the Earth would likely pass through it, but it will be unimpeded. Next. I think you're muted.
Oh, yeah. Yeah, so let's talk about the previous experiment, because as we talked about generation and detection, so we talked about that these particles are extremely difficult to detect, and extensive experimentation are going around it in order to detect it. And among these experiments include Atlas detector, Moidal detector, and heavy ion collisions. The first one, Atlas detector, as we talked about, LHC is a big infrastructural apparatus, and Atlas, which is the opening is autoradial LHC apparatus, is one of the largest and most flexible detectors, and its general purpose detector at LHC. And in Atlas, numerous specific searches for monopoles have been performed with the utilization of samples of data obtained by high-energy proton-proton interactions. This was accompanied by tracking systems and have greatly improved the sensitivity to rare and exotic particles. But however, the searches for monopoles have not been successful and have not provided aspects of monopoles up to date. But the searches have certain cross sections and masses of monopoles, which is beneficial for the field of science. So, and the second one is Moidal detector. And Moidal detector is the opening is monopole and exotics detector, LHC, is in the search for magnetic monopoles and other highly ionizing particles. And several methods to identify monopoles are used in Moidal, and they include plastic nuclear track detectors and trapping volumes. And in the absence of and Moidal is still on the absence of any monopole discovery so far, but has expanded the scope of detected capacities and give fairly tight constraints on the various theories. And the last one is heavy ion collisions. And the heavy ion program of the LHC, especially by the ALICE experiments, explored the appearance of monopoles in gargantuan magnetic fields created during heavy ion collisions. As also, these experiments have not detected any monopoles yet, but ongoing research improves the understanding of and the methodologies. And the future plans. And the future plans at CERN in order to find the monopoles. The first one is high luminosity LHC, and this LHC plan to increase the collision rates and the data volume after 2029, and high luminosity LHC is planning to provide a much higher interaction rate at the LHC, thereby providing better chances for the observation of monopole production. And based on the data, it's planning to give 10 times more data than the current LHC that's used for detecting the monopoles, thus improve the monopole search sensitivity by 10 times. And the second future plan for the detection of monopoles is upgraded Moidal detector, and several in this upgraded version of Moidal detector includes improvements to Moidal about its sensitivity, and it includes new nuclear track detectors, new time pixel detectors, and new data acquisition systems. And these improvements planning to be useful for experimenting and for enhancing identification and for the monopoles. And the last one is advanced detection techniques, and this one this is about improvement of detection techniques, and which includes the development of high precision timing detectors.
and improve data analysis algorithms and machine learning techniques for identification. As the machine learning improves day by day, this is also planning to be used for detecting the magnetic monopoles. And let's go to the conclusion.
So the quest for to detect magnetic monopoles began in the 60s when scientists and physicists just observing them experimentally. And three experiments, Atlas, Model, and Alice, each one employing a different method to transform energy into matter, represent significant effort in this pursuit. While none of these experiments have yet detected any magnetic monopoles, they have advanced both experimental and theoretical boundaries in electromagnetism. And as my friend Sabina said, these pioneer experiments have paved the way for future studies at the LHC, which include prospect of higher collision rate, increased data collection, and improved detection techniques. So overall, the experiments have been successful in contribute knowledge and methodical innovations in the field of electromagnetism. So that's all. Thank you for your attention.
Thank you so much for listening us.
Okay, lovely. Does anyone have any questions for the experimental and engineering team? Okay. I really like that the cosmology team talked about the quantum side of their research and the E&E team talked about the cosmology side of their research. So, sorry, the cosmology team talked about the quantum side of their research and the E&E team talked about the cosmology side of their research. That shows how all the fields of physics are connected. I really, really like the practical explanations of it as well. So you guys explained how each detector works, which I found brilliant, to be fair. Superb teamwork from you and fantastic presentation. So I want to say well done, experimental team. Now we will have a 10-minute break because today is full of scientific presentations, and normally in academic settings, it's like, 4 hours of non-stop presentations, but I don't want to do that to you yet. You will see this further in life anyway, so we can just take a 10-minute break here and then we can come back at past 30. Okay, I'll see you in 10 minutes. Okay, and we're back. Just to wait a little bit for everyone to be here. A minute. Okay, now it's past 14, so we will continue. I'll hand it over to mathematics students for the presentation of their research now. But first, I will hand it over to their mentor, Ethan. If Ethan's here.
Hi. Yeah.
Hello, I'll hand it
Like,
over to you now.
okay. Hi guys. So, yeah, I think it's just been a really fun and interesting experience this past like 5 weeks, just to talk to everyone and learn more about this area that we're doing. And just a quick introduction about what we did in the past 4 weeks is that we studied graph theory, which is the study of essentially relationships between different objects in a sort of system. And you can kind of guess that this has quite a lot of different applications, but the one that we did, the application that we mainly focused on is concerning like just how Google works and just the algorithm that goes behind it and the mathematical aspects that relate to Google. And yeah, so I'll hand it over to you guys for the presentation.
I was wondering whether you could share because my computer's a bit laggy.
Guys, are you sharing a screen or is your mic on? Because we can't hear anything or see anything from you for now.
I think there's just some slight technical issues.
If you want, I can share
Okay.
the presentation in the chat and maybe Arya can share it if.
Of course, yeah.
Yeah, I'll share it in the chat.
Okay, I'll be sharing the screen, but I requested to see it first, so
Oh
that I
no,
can share it.
Yara's got the permission and she's not here. Let's see if I can. You know what?
What we can do.
I'll try sharing it.
What
But
we
if
can.
I drop out of the meeting, then obviously that's because my computer's gone off. So
Okay, what we can do is we can move to the quantum physics presentation first, and then you guys can go last if you want more time.
I don't mind. I can share my screen, I think.
Oh, you can. Okay, brilliant. Then hand it over to you guys.
So as you know, we worked on graph theory, and sadly some of our group members weren't able to attend. So Ethan, do you want to? So we're going to talk about artificial intelligence algorithms. Dictionaries are algorithm used in Google Maps and Google's PageRank algorithm. Ethan, do you want to do Casey's bit? Or should I do that? Am I still sharing?
Yes.
Yeah, okay, so then I'll just read this bit then. So we've got some, so as part of the research, basically Ethan taught us quite a lot about matrices and graphs, and so here we've got some definitions. So like a graph is an ordered pair comprising of vertices and edges, so objects and relationships between objects. So a weighted graph refers to where weights are assigned to each edge, and they can be represented by directed graphs where the edges have arrows that show the path direction, and undirected graphs where edges are bidirectional and have no arrows. So here we have about a part about artificial intelligence AI algorithms, which Casey unfortunately couldn't join us today. So we've got, wait, is there something in the chat? Sorry. So we've got what is AI? What is an AI algorithm? 4 types of AI algorithms and uses of AI algorithms, as well as graph theory in AI. So AI is the science of making technology think like humans. So AI solves problems, learns from data, and mimics human actions. So the term was coined by John McCarthy in the 1950s, who believed machines could one day simulate human intelligence. AI has many applications and is an evolving field of study. So an algorithm is a set of instructions to be followed when solving calculations and other problems. An AI algorithm is a set of rules that programs the computer to operate on its own. This allows the machine to learn, analyze data, complete tasks, and make decisions based on its knowledge. Without an algorithm, AI wouldn't exist. So there are 4 types of AI algorithms, so supervised learning, unsupervised learning, both supervised and unsupervised, as well as reinforcement learning. So supervised learning is like a student learning in the presence of a teacher, so labeled data is presented and used to learn and predict outcomes from other sets of data. And data scientists are present to correct errors and check accuracy. Unsupervised learning is unlabeled data being presented and used to evaluate the relationships between different sets of data. So supervised and unsupervised learning is both labeled and unlabeled data is given, and reinforcement learning is when the AI learns by receiving feedback from results of the action. And there are lots of different algorithms under these categories, some of them which we will detail later in the presentation. So there are search engines such as Google, Bing, or Yahoo, so they're digital assistants which we know of, such as Alexa, Cortana, and Siri, and their applications in robotics like self-driving cars. So graph theory in AI is what we've is a specific area of interest which we talked about as a group, and since obviously that was the main section we were researching, this field of mathematics. So graph theory is applied in AI in a multitude of different ways, such as social network analysis, so finding connections within social networks, recommendations, so predicting a user's preferences by considering connections between users and searches, knowledge graphs, so presenting information in a way machines can understand and make inferences about, molecular modeling, displaying molecules as graphs to predict properties and interactions, route selection, finding the shortest and most efficient routes in logistics and transport. So now we have the second part of the presentation, which Chiara recorded her part. Let me know if you can't hear. Can everyone hear me?
Hi everybody, I'm Chiara from Italy, and the first thing I wanted to say is that I'm really sorry for not being able to take part in today's final presentation and for missing the opportunity to meet you all and to listen to your works. Anyway, I hope you'll enjoy this alternative way I found for presenting my part, which is the use of Dijkstra's algorithm in Google Maps. Graph theory is also used in Google Maps to find the most convenient way to go from a place to another. In fact, to find the shortest path to reach the wanted destination among all the possible ones. The web service uses Dijkstra's algorithm. This algorithm was developed in 1956 in Amsterdam and takes its name from its inventor. Let's now see how the algorithm works. The aim of Dijkstra's algorithm is to find the shortest way connecting two vertices of a weighted graph, so the path that minimizes the sum of the associated weights. The starting vertex is called source vertex. To use it in Google Maps, we have, of course, to interpret the network of roads as a weighted graph, in which each crossroad or corner is a vertex, and each road connecting two of them is an edge with an assigned weight as distance or time needed to go from a vertex to an adjacent one. Let's now get deeper into the topic. Basically, the algorithm assigns a cost to each vertex, representing the shortest way to reach it from the source, until the destination vertex is reached. In this way, it manages to find out both the shortest and most convenient path and the value of the distance or time needed to get to the destination. More precisely, first of all, we select the starting vertex and the ending one, and we associate a cost 0 to the starting vertex. In fact, the time or distance needed to get there is of course 0 since we are already there, and a cost infinite to all the other vertices. That just means we haven't found an estimate value of the shortest way to reach them from the source. Then, from the starting vertex, we assign a cost to all the adjacent vertices equal to the value of the path needed to reach them from the source. Afterwards, after we select the vertex with the lowest cost associated, we mark it as visited. That means that we have found the shortest way to reach it from the source. Anyway, we also keep track of the values assigned to the other vertices, even though they haven't been marked as visited yet. Afterwards, we repeat step 3 and 4 with all the vertices adjacent to the last visited vertex. Sometimes it can happen that there are two possible ways to reach one same vertex, and so two possible costs that we can assign to one same vertex. In this case, we choose the lowest cost. That's equal to the value of the minimum path we can use to reach it from the source. We stop when the destination vertex is reached and marked as visited. In fact, the cost associated with it is equal to the value of the distance or time needed to get there from the source, while the minimum path which leads to that vertex is given by the set of edges which have been summed to obtain that cost. Lastly, let's see an example on a weighted undirected graph. So, in the first place, we choose the starting vertex A and the destination vertex F, and we assign a cost 0 to the source and a cost of infinite to all the other vertices. Then we assign a cost to all the vertices adjacent to A, so B, C, and E, that's equal to the value of the edge connecting them to the source. 4 for B, 3 for C, and 7 for E. We notice that the vertex with the lowest cost associated is C, and we mark it as visited. Now we see that the unvisited vertices adjacent to C are B, D, and E. We now have two new ways to reach vertex B and vertex E, by following the path ACCB or by following the path ACCE. Anyway, if we chose one of those, we should assign a new cost of 9 to B and a new cost of 11 to E, which are both higher than their actual ones, so we don't update them. We just assign a cost of 14 to D. Afterwards, we select B and mark it as visited, since it's the unvisited vertex with the lowest cost associated. We now see that the only unvisited vertex adjacent to B is D, and that the new value obtained by following the path ABBD would be of 9, which is lower than 14, its actual value. So we update it. Then we select E and mark it as visited. The two unvisited vertices adjacent to E are G and D. However, since the value of D remains of 9, even if we choose to follow the path AEED, we just assign a value of 12 to G, and then we add D to the list of the visited vertices. Lastly, we assign a cost of 11 to F, since the new cost associated with G would be of 19, which is higher than 12. Then we mark F as visited, and we can stop the algorithm. We have reached the destination vertex, and we have found both the minimum value, which is 11, and the minimum path, which is ABBDDF, to reach it from the source. And that was all about Dijkstra's algorithm used in Google Maps. I hope that was clear, and I wish you all a great summer. Goodbye, everybody. Ciao a tutti.
So thanks to Chiara for that. And okay,
Hi, everybody. I'm Chiara from Italy, and
so the next part is Google's PageRank algorithm. So Google's PageRank algorithm, named after co-founder Larry Page, is an algorithm used by Google which attempts to determine the importance of a website. So search engines display results to searches. So if you search, for example, Hello World in Google, it displays the searches by placing results in a ranked order, with results which are more important or more pressing at the top of the page, and results which are not deemed as important in the deep dark corners of the web. So graph theory is evident in Google's PageRank algorithm, and I'll be discussing the criteria of the importance of the page, how the problems with the criteria are solved, and the example of a random surfer model, and a graphical representation of the algorithm. So the definition, but first, how can we determine the order of pages if we don't even have a criteria for classifying the importance of a page? Pages on the internet are sorted into intricate webs of links depending on the user's search, like the example on the right of the slide. Since pages are connected to each other by links, the algorithm assumes that if a page is linked to many pages, it's probably more important than a web page linked to fewer pages. Therefore, the leftmost page is deemed most important by the algorithm since it has the greatest number of links. And with converse reasoning, the bottom right page is classified as the least important in this network. So let's simulate how this would work without any additional algorithms. We are using a bot which randomly jumps to a page in the network. However, pages with the most links have a higher chance of being chosen by the bot. I'm going to close this tab, it's so annoying, sorry. So let's just see the bot moving from page to page. So let's fast forward and see the final rankings of the page. However, evidently, two problems have just arisen. The first is that the bot cannot reach the separate networks. The network on the left is more densely linked and there are no links between the network on the right. Secondly, it's extremely easy to inflate the importance of a web page with just the above categorization of importance, as you could create web pages linked to a site you want to be deemed more important, or you can employ tactics such as spoofing to illegally advertise, etc. So therefore, we can create a more nuanced definition. So the more important a page is, the more links it has to other important pages. But doesn't this create a paradox? So how can we calculate the importance of a page if calculating the importance of a page requires knowing another page's importance? Well, there is a rather simple explanation to this, and it's using the random surfer model. The random surfer model repeats the process of randomly switching to another page which the page is currently linked to, based on the amount of times the random surfer lands on a particular page in the network. So essentially the random surfer jumps from page to page in the network. However, there is a random factor which causes it to go to different pages and keep track of how many times the page has been visited. So we need the random surfer to ensure that it goes to the second network. So the inflation of a page's importance has been solved by this nuanced definition of an important page. However, another factor needs to be added in order to solve the problem of the random surfer not jumping to the second network. And this factor is called the damping factor. The random surfer will switch to a page on the internet chosen totally at random and not within the current network, leading to eventually all the pages on the internet being visited and their relative importance deemed by the percentage of the page being visited. Directly linked pages, for example, the one which has 1,989 in the original part, has more of a chance of being visited, as you can see, with an 85% chance in this example. So let's see the bot moving from page to page. As you can see, there's an 85% chance that it will move to another page in this particular network. However, there is a 0.15 chance that it will jump to the second network, but a 0.85 that now that it has jumped to the second network, that it will remain in that particular network. So let's fast forward and see the final rankings of the page. So percentage values will be calculated to the random surfer's movement, and therefore these pages can be ranked in importance. So that's how millions of results from a Google search are ranked, with probably the most trustworthy or the most popular sources at the top. Of course, the algorithms on the previous slides and the examples on the previous slides are simplified due to the volume of the internet and the complexity of this algorithm. However, I wanted to use some sources on the internet to further solidify the link between graph theory and the algorithm, as a simple representation does not do the ingenuity of the algorithm justice. For example, one of the sources which Wikipedia uses on its page on the algorithm has a simplified Python code importing PageRank algorithms. Moreover, Princeton's online course details how matrices are used with a random surfer to classify the randomness of it, which links to parts of the content which Ethan taught us. And finally, if this topic has caught your interest and you're interested in learning more about the PageRank algorithm, I would recommend starting off in this interesting topic by watching the video made by the Spanning Tree YouTube channel and reading through the PageRank section of Harvard's CS50 Introduction into Artificial Intelligence Python course. So I want to thank Ethan for the amazing lessons which we've had, and I wanted to now hand over to Samuel, who's going to share his part of the presentation.
Okay, are you guys able to see this?
Yes.
All right. So starting here. So influence of algebraic connectivity on PageRank. So firstly, spectral graph theory is a powerful tool for analyzing the properties of graphs through the eigenvalues of matrices like the Laplacian matrix. Within this context, algebraic connectivity is defined as the second smallest eigenvalue of the Laplacian matrix. This metric is crucial as it measures the connectivity and structural integrity of a graph. So essentially, a higher algebraic connectivity implies a more connected and resilient network, which is fundamental for ensuring the reliability and efficiency of various network operations. So its impact on PageRank algorithm. So the PageRank algorithm, famously used by search engines such as Google to rank web pages, is significantly influenced by the algebraic connectivity of the network it operates on. So specifically, this study investigates how the algebraic connectivity affects the algorithm's performance in terms of conversion speed, stability, and accuracy. So conversion speed refers to how quickly the algorithm can compute the rank of pages. So while stability pertains to its ability to consistently produce the same results under various conditions, accuracy is about how well the algorithm produced the same results about how well the algorithm can rank the pages in order of their true importance. Higher algebraic connectivity tends to improve all these aspects, resulting in faster, more stable, and more accurate PageRank computations, which is crucial for different information retrieval in large-scale networks. So, real-world applications. Firstly, the implications of these findings are extensive and impactful across multiple domains. First, in the context of network resilience. So understanding and optimizing algebraic connectivity can help in designing networks that are more resilient to failures, such as the loss of nodes or links. So this is particularly important for maintaining the functionality of critical infrastructures like communication networks and smart grids. In information retrieval, optimizing algebraic connectivity can lead to more efficient and accurate search results, which improves the performance of search engines and recommendation systems. Moreover, in practical applications such as hierarchical communication networks and smart grids, maximizing algebraic connectivity can enhance the strength of network and traffic management, which contributes to the overall efficiency of these systems. So by integrating the principles of algebraic connectivity into the design and analysis of networks, we can develop systems that are better equipped to handle the complexities and challenges of modern information and communication technologies. So algebraic connectivity plays a key role in web search engines like Google's PageRank algorithm. So by improving the connections within the web graph, search engines can provide more accurate and faster search results. This means users get better information quickly, making their search experience much better. So higher connectivity helps the algorithm rank web pages more consistently and reliably, which ensures the search process is efficient. Now, in social networks, algebraic connectivity is important for spreading information effectively. So platforms like Facebook, Twitter/X, can use strong connectivity to make sure news and viral content reach users quickly and efficiently. This helps maintain strong communication, even during high traffic or disruptions. So by using algebraic connectivity, social networks can improve how they share information and stay resilient against interruptions. So moreover, telecommunications networks benefit greatly from great connectivity. So high algebraic connectivity ensures that data is sent reliably and efficiently. Even if some parts of the network fail, this is crucial for companies like AT&T and Verizon, which rely on stable and continuous communication services. So by optimizing connectivity, these companies can provide better service, reduce downtime, and improve overall network performance, which leads to happier customers and a stronger infrastructure. And that's it. Thank you so much for listening. I would like to thank our research mentor, Ethan Lee, and our whole group. Any questions?
Wonderful. Does anyone have any questions for the mathematics team? You can just speak up if you have a question. You don't have to raise your hand. Let me check. But I have a question. So you guys talked about the damping factor. Was that a good thing or a bad thing? And is it like a percentage wise damping, or what kind of damping is it?
So I think I can answer this question. So the damping factor, so the example which I used of 0.85 and 0.15, that was completely random to my example. However, as part of the PageRank algorithm, they do have a damping factor, and the damping factor essentially is to ensure that the random surfer moves to different networks, even if it isn't directly connected by a link. So the damping factor essentially means that obviously if you've got these two networks, which are two separate networks, as you saw on the left and on the right, the random surfer model obviously wants to move to the pages which it has direct links to, because it's easier to do that. However, the damping factor means that every so often it will move to the other side, and therefore this damping factor, I think, is usually a small number, but the damping factor essentially ensures that the random surfer can access and explore all the pages on the internet, because obviously you have to remember the PageRank algorithm doesn't just visit a page 3 times, and like the most densely populated page isn't visited 10 times. It's visited like hundreds and thousands and even millions, because obviously this is how huge the internet is. Does that make sense, or have you got any more clarifications?
That makes sense. Yeah. Yeah, that was brilliant. So you have missing members, but I think you have handled it very well, by the way. Does anyone have any other questions for the maths team? Nope. Okay, so I just want to add a few comments. I think it was a remarkable analysis of the AI systems and Google algorithms, and your insights into complex material were very impressive as well, and insightful. Now I want to move on to our final team presenting their research. It's the quantum mechanics students. I have mentored quantum mechanics students over the past 5 weeks, and they have been nothing but remarkable. They were absolutely brilliant, like many of you here. Over the past 5 weeks, in the quantum mechanics course, we talked about probability functions, Schrödinger's equation, quantum tunneling, postulates of quantum mechanics, Bell's inequality, to quantum computers and black hole information theory. And we learned that black hole is actually a giant quantum computer. So we did a bit of cosmology as well, but obviously the 90% of the course was mainly quantum mechanics, quantum entanglement, and how they're mathematically and conceptually contextualized. So I'll hand it over to them now to show their amazing work they have come up with. So I'm handing over to you, quantum team.
Yeah, so I'm gonna share my screen. Let's see whether I can make it a full screen. That'd be good. Okay. Is that a full screen? Did it work? Okay. I'm gonna assume yes. So our
I don't think we can see Katie.
Can't you? Okay. Clicking on. Okay. 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 Is that working?
Can you please? Did you click the slideshow?
Yeah.
No, we can just see the first page and the.
Yeah. Yeah, I'm not sure that it's gonna let me go on to slideshow.
Okay.
Can you see Can you see it change?
Yeah.
Yeah. Okay, cool. That
Okay.
works.
That works.
Yeah. So we did it on interpretations of quantum mechanics. So so basically what that means is that there are different different ways to describe like the way the way when we observe there are different mathematical models which describe the way we observe reality, and no one's been able to decide which one's correct because that's kind of and because just they all have different things that work and different things and that don't work. But we're going to talk through which interpretations there are. Yeah, Beatrice, I think this is you.
So we'll mainly focus approach of patient absolute. In the beginning of the interpretations of quantum mechanics, the only part was the time interpretation, and the collapse happened because of a measurement made by an observer. Some of the scientific evidence happy about this, and so interpretations came up, and there are interpretations that can be, and by more realists, what is meant is that what is described by quantum theory really exists and has definite, even when they're not at it. And so the observer doesn't play the same role as it does in collapse, an interpretation that's collapse. So we'll start with the Copenhagen interpretation, and then go to the many worlds interpretation, then the transactional RMP continued model. I wanted to show some properties lists. So the main differences are in how each interpretation has first is the nature of reality. For the realist, it's a definite particles all having precise properties, and in an interpretation that involves labs measurements. The wave function for the realist interpretation is a guiding field, so it doesn't collapse. And in collapse interpretation, it collapses upon. Now, measurement feels since the system has those definite properties, even when an observer, when a measurement is made, we're just measuring the properties, while a collapse interpretation, the measurement creates, and this poses about the nature of reality. Now, the realist interpretation is determined. So, past and present affect outcome. So you can determine things by the past and present. While in collapse interpretation, only have probabilities. So the outcome is deterministic. Now, in terms of non-locality, non-locality is a strange term, and it's about the apparent ability of objects to instantaneously know about each other's state, even when they're separated by quite large distance. And then the role of the observer, which is in the realist, it does not affect outcomes, while in collapse interpretation, it's very important. It's an active role, and it acts. And finally, the evolution of a system. In the realist interpretation, it always follows the Schrödinger equation. And the collapse interpretation follows the Schrödinger equation plus a collapse possible. Now
the Copenhagen interpretation was formulated in the 1920s by Niels Bohr and Werner Heisenberg, and it's one of the most, if not the most, widely taught and discussed interpretations of quantum mechanics, and it's probably the one from which most people will recognize a couple of the key concepts for. In the Copenhagen interpretation, the state of quantum systems is described with a wave function, which encodes the probabilities of all possible outcomes of a measurement. The probabilities of the outcomes are given by the square of the amplitude of the wave function, and this concept is called Born's rule. Before measurement, a quantum system exists in a superposition of multiple states simultaneously. Now, this concept of superposition is often explained with the thought experiment of Schrödinger's cat, which most of you will have heard of. In this thought experiment, you imagine a cat placed in a sealed box and a tiny bit of radioactive material so small that in the course of 1 hour, there is a 50% chance that one of the atoms decays and a 50% chance that it doesn't. And in the box, there is also a Geiger counter, and if the radioactive atom does decay, it triggers the Geiger counter, which is connected to a mechanism that will release a hammer, which will smash a vial of poison, killing a cat. I don't know why the thought experiment had to be so elaborate, but it was. And in this thought experiment, due to the superposition principle, the cat inside the box is simultaneously in a state of being alive and being dead until an observation is made. Now, I'll come back to this thought experiment shortly because it also illustrates the wave function collapse, which I'll now talk about. When a measurement is made, the wave function collapses into a single eigenstate corresponding to the observed outcome. This process is instantaneous and results in one definite state of the quantum system. And you can see the change in wave function in the big picture in the top left of the slide. Now, coming back to Schrödinger's cat, this can be demonstrated as when the box is opened and an observation is made, the superposition of the cat collapses into one of the two possible states, either the cat being alive or the cat being dead. Now, another key concept in the Copenhagen interpretation is complementarity. Now, Bohr introduced this concept, and it states that objects have complementary properties that cannot be observed or measured simultaneously. For example, the wave and particle nature of light are complementary aspects. The type of measurement performed determines which aspect, wave or particle, is observed. For example, when observing the photoelectric effect, which you can see in the bottom right, using maybe a gold leaf electroscope or another experimental setup, the photons and electrons behave in their particle nature. However, in the young double slit experiment, which you can see on the right-hand side of the slide, we observe the wave-like behavior of particles. Now, moving on to a concept that most of us will probably have heard of is Heisenberg's uncertainty principle, which we can see in the bottom left corner. On the left side of the equation, we have delta x, which represents the uncertainty in position of the particle, and that is multiplied by delta p, which represents the uncertainty in momentum of the particle. And on the right side of the equation, we have Planck's constant over 4 pi. This right-hand side of the equation could also be represented as the reduced Planck's constant, which I think the experimental team mentioned over 2. Now, this principle asserts that for a certain pair of physical properties like position and momentum, they cannot be precisely measured at the same time, and there is always an inherent uncertainty in these measurements. The more precisely one property is measured, the less precisely the other can be known, which is made clear in the equation because the product of the uncertainties of the two properties is greater than or equal to the right-hand side. This principle is in fact not unique to the Copenhagen interpretation, but in the Copenhagen, they emphasize that the uncertainty principle is a fundamental limit on what can be known about a system, and it interprets the principle as reflecting the non-existence of definite properties to prior measurement. Now, when I first came across complementarity, I was often getting it confused with the uncertainty principle because, when it's written down, it looks quite similar. But to clarify, the difference between the two is that in complementarity, the properties cannot be observed simultaneously for experimental reasons. So you can't observe the wave nature and the particle nature at the same time. Whereas in Heisenberg's uncertainty principle, it has nothing to do with experimental limitations, but it's a fundamental property of nature that they can't both be known with certainty. Next, I'm going to move on to the quantum classical divide in quantum mechanics. The Copenhagen interpretation maintains a clear distinction between the quantum world, which is obviously described with wave functions and probabilities, and the classical world, which is described by classical mechanics. And because of this distinction, classical measuring devices and observers are needed to make sense of quantum phenomena, but they themselves are not described by quantum mechanics. The act of measurement by an observer plays a crucial role in determining the outcome of a quantum event because the observer and their act of measurement causes the collapse of the wave function and brings the system into a definite state. This interpretation has in the past and continues to this day to provoke scientific and philosophical debates on a variety of its concepts, and most famously between Einstein and Bohr about the questions that arose from the impact of the observer on the wave function and the nature of reality, and their resulting debate about realism versus anti-realism. Einstein wasn't a fan of the Copenhagen interpretation because of its anti-realist perspective, and most of you will have heard the famous quote, "God does not play dice." And that was his view on this interpretation. So not everyone agrees with it, not everyone likes it because of its anti-realist stance, but yeah, that's the Copenhagen interpretation. Next slide, Katie.
Yeah, so the transactional interpretation interprets wave functions as physical waves and it talks about completed quantum events as a next change between the advanced wave, the wave kind of going backwards in time, and the retarded wave, the wave going forward in time. As that being the transaction or the handshake, as it's known, and that's the basis of this interpretation, is that wave functions are those are those physical waves being exchanged, and this photo comes from the Wheeler and Feynman approach, which is a theory in dynamics, which uses this interpretation. It solves the problem of interaction, and because it has two distinct waves, the advanced wave, and by the absorber going backwards in time, and then the emitted wave, and by the emitter going forwards in time, and known as the retarded wave, and then that's how electrodynamics works in this theory. And those two waves like interacting, and then these equations here are the equations where you get the waves from. Schrodinger's equation just basically describes how a quantum state evolves in time. The I it's like I equals root minus 1 h bar is the reduced Planck constant, what's that, like theta over theta t, or maybe a delta over delta t is the is the partial derivative of time, and h the capital H is the Hamiltonian operator, and the phi xt is the wave function, so that's the retarded wave, which assumably has solutions like forward in time, and then the phi asterisk is the complex conjugate, so it's the opposite. Like I'm going backwards, going backwards in time. So that's that wave function, and that and then that physical wave, and this interpretation is non-local, so the waves can affect each other even when they're spatially separate, so when they're not next to each other, and then it's also relativistically invariant, so it doesn't change depending on the reference frame of the observer. And yeah, that's the transactional interpretation.
Okay, so moving forward, this is the many worlds interpretation, which is another theory that we've discussed, and it was developed by Hugh Everett in the 1950s. This theory addresses some of the fundamental paradoxes in quantum theory, but especially the multiple observer paradox, which traditional interpretations have struggled to explain. The main issue for which this paradox was struggled to explain by traditional interpretation is because of the measurement problem. In fact, in classical quantum mechanics, the measurement phenomenon causes the wave function to collapse, as explained by Ali earlier. However, in an environment in which there are multiple observers observing the same quantum system, we cannot have multiple measurement, as they would cause multiple collapses of the same wave function. So this description couldn't be allowed within traditional terms. So how this collapse can reconcile with multiple observers? Hugh Everett, with the many worlds theory, suggested that the wave function, rather than collapsing, undergoes branching, as you can see in the picture. And this means that each possible outcome of a quantum event can occur in its own separate branch of or world. In this way, every time a measurement is made, the universal wave function splits into different world functions, each representing a different outcome. About the branching of the wave function, we need to state that according to the Schrödinger equation, the evolution of the wave function is linear, as you also can see in the picture. Instead of collapsing upon measurement, the wave function branches into different possible states, and each branch corresponds to a different measurement or outcome, as I said. And these branches or worlds evolve independently one another. According to Everett, the relationship between the observer and the observed system is critical because the observer and the system form, as he said, a composite quantum system as a mathematical description, meaning that both the observer and the observed system are considered to be subsystems of the same composite quantum system. So there's the superposition of their two states can be described by the combined wave function, which can be seen on the bottom right corner of the presentation, where the term phi to the ith power of x1 represents the ith state of the first subsystem, or the observer, and eta to the jth power of x2 represents the j state of the second subsystem, or the observed system. This wave function helps us understand how the observer state is linked to the system state, and how in this measurements process, the interaction between these two subsystems leads to entanglement. So this interaction basically leads to results in a coherent and consistent picture of quantum phenomena. However, this interpretation has some meaningful implications. Due to the entanglement of the states of the subsystems, neither the observer nor the system holds an independent state, meaning that they exist as part of a unified state described by their combined wave function. In practical terms, although each branch of the wave function represents a distinct outcome, only one outcome is observed in each branch. And this aligns with our experience of reality, where despite multiple possible outcomes, we observe only a single one. And this makes this interpretation a realist interpretation. In short, the many worlds interpretation offers a consistent interpretation of quantum mechanics by proposing that all different outcomes of quantum events occur in separate, non-communicating branches or worlds. And this explains the probabilistic nature of quantum mechanics while aligning the results with our observed reality. So that's it. I'm handing it over to Beatrice.
So the continuous localization model was a model that was created because a previous model was giving physics. Model was RD, and the two main problems that thankfully are by the continuous were that they weren't able to alike particles, meant that system, if they weren't able to treat alike particles, that meant that they particle, each type of particles and the behaviors of particles to for the collapse of wave function and for the collapse to be. And so the collapse model of the continuous localization array, and any collapse model wants problem by superposition is and when a microscope interacts with macroscope, that the wave function. This model provides a continuous wave function, and it's spontaneous localization because there are random collapses that occur, and they are spontaneous. And one important fact is that for this to happen, there was introduced a term in evolution that was called the noise field term. Now, this noise field term sometimes is described as stochastic, is very words that well, it doesn't mean anything until actually applies us to this. So for the collapse to happen, this evolution, you can do thought. Imagine you have two friends that are walking. They have one coin and they decide to play a game. If friend one gives a point to friend two every time adds, and friend two gives a point on every time the tiles, for a large distance that they're walking, at some point one of them will have 100. And let's say the game finishes when one of them has 100. Over the duration of the game, there will be fluctuations in the number of points it has. But the game only ends when one of them has 100. So these fluctuations are what happens when the noise field is interacting with the system. It's like a random walk, and the noise causes light to change randomly, and the particle slowly settles, either spin up or down state. So this collapse is not merely a change in the observer's knowledge about the system. It represents a physical transition from a superposition state. And that's what makes the continuous localization model a realist implementation. It allows for a continuous collapse and the gradual transition states, and the localization rate depends on mass. So heavier objects localize faster than lighter objects. Now, one of the main things I learned in the course was not be scared of big equations. And so please don't be scared by this big. It is merely a one of the standard equations that represents the stochastic nonlinear that allows for it. So first of all, H with a hat is the Hamiltonian system. An important term is the DWJE, which is the independent binary process. It means nothing, but it represents the random noise of the system. It's the interaction between the system and the then the A with hat and J are the localization of they're typically chosen and a hat J is a quantum expectation value of AJ. Simplify, this term is what ensures the norm of the wave function and it counteracts the the main problem with that, because of this interaction with there's an unlimited increase in energy. We all know it's and therefore for research so which will be tensions are the dissipative CSL model, which introduces a term that balances the energy and basically they aim to address this by introducing mechanism that will allow the system. Now the very big innovation at the end is the non-linear damping. This is a term that compensates for the diffusion introduced by the stochastic term and ensures that the total probability remains constant.
Yeah, that was us. Thank you, Arya. You've been amazing.
Yeah, thank you. So does anyone have any questions for the quantum team? Let me see. No questions today, except me. Okay. So I must say that's a brilliant piece of research, quantum mechanics team. I really like that you delved into the interpretation of quantum mechanics in this context of wave function collapse. I think that's really impressive and insightful. Now, this was our last presentation, and I liked each of them. I'm really proud of all of you guys. And now with the last presentation, we have come to the end of our night. I mean, night for some of us, of course. Some of you maybe is early in the morning. I would like to thank some of the people to working on the RMP. So I would like to thank my mentors first again for making the lectures possible. And I want to thank our head of marketing as well, Chiara Allegri from here. She's not here right now, but if you interacted with our Instagram, you probably interacted with her. She worked brilliantly in the marketing department. I would also like to thank Eleonora Swanberg as well. future Dr. Eleonora Swanberg of Theoretical Physics. She's now in Oxford doing her PhD. I met her at a conference at King's, and I asked her if she could promote the program, and she said yes, just immediately. So I want to thank her from here as well. Okay. Do any of the mentors want to add something before I move on to the final piece of the night? Let me check. No. Do any of the students want to add something before I move on? No.
I just
wait.
wanted to thank you and all the mentors for this amazing opportunity you offered us. We had the opportunity to delve into difficult topics that we don't usually encounter at school, and also to make some unforgettable friendships with people from around the globe, all around the globe. So thank you for that.
Thank you for that, Giuseppe. That was very nice. That's really nice to hear as well, because that was the purpose of the program. And yeah, so each of your pieces of research, I'd say they're truly remarkable, and they will find their place in the RMP Science magazine. So I'm trying to make it published around the end of August, but I'll let you know as soon as it's published, and as soon as it's published, I'm going to publish it on Discord as well. If you like the program, please recommend to a friend interested in physics. We would always welcome more applicants. I will also send the feedback form after the meeting to take your views under consideration. So I will also attach to the email, which I will send out your certificates with. So I will send them shortly. Okay. Let me snap a photo before I move on. Can everyone turn their cameras on for 5 seconds, please? I'll wait for like 10 seconds for everyone to open their cameras.
I don't have a camera, just let you know.
Sorry?
I don't have a camera, so I can leave and come back. I'm not
It's okay, yeah.
You sure?
Yeah. I mean, if people can, that'd be great. But if you can't, that's okay as well. It's not mandatory. Yeah, I assume that people who could turn their cameras on did. So I'm just going to take a picture. As soon as it loads for me, shaky Wi-Fi is always our biggest enemy, I think. Okay, lovely. I snapped the pic. Brilliant, thank you. For final words, I hope all of you enjoyed RMP 2024. Hopefully I will see you soon, probably in an academic setting, maybe not in an academic setting, but most likely, I think, because you all have very bright futures ahead. And we can keep using Discord. If you come across an interesting paper or a random maths problem, don't be shy, just share it with everyone. You're free to use Discord after this program concludes. Like I said, you will receive your certificate soon. And don't refrain from connecting on LinkedIn with me, your mentors, and with each other. Keep connected with yourself. Okay, so take care, everyone. Now you have become you're all RMP alumni, I'd say. Okay, hope you all enjoyed the program. Now I can just say goodbye and end the meeting. Bye-bye.
Thank you. Bye.
Bye-bye.
Giuseppe,
Bye.
very good,
Thank
very
you.
good.
Thank you very
Thank
much.
you.